Given the matrix A, 2 by 2, where the first row is 4, 6, the second row is 1, 3. The matrix H, also 2 by 2, the first row is 3, 1, and the second row is 2, negative 1. And we're asked to compute the product A times H. We can perform the matrix multiplication if the number of columns in the first matrix is the same as the number of rows in the second matrix. For the first matrix, A is at the dimension 2 by 2, and the second matrix has the dimension 2 by 2. There are 2 columns in the first matrix and there are 2 rows in the second matrix. So yes, we can perform this operation. We then write AH side by side. First, we write the matrix A, which is 4, 6, 1, 3, and the second matrix 3, 1, 2, negative 1. To multiply the two matrices, we would take the first row in the first matrix and multiply the first column in the second matrix. This is why we require that the number of columns in the first matrix to be the same as the number of rows in the second matrix. This is known as the inner product, where we take 4, 6 as the first row and multiply the first column 3, 2. Now this operation only gives us one number. We take 4 times 3 plus 6 times 2, which is 12 plus 12, or 24. Next, we take the first row, which is still 4, 6 of the first matrix, and multiply the second column of the second matrix, 1, negative 1. This is 4 times 1 plus 6 times negative 1, or 4 minus 6, which is negative 2. Next, we take the second row in the first matrix, which is 1, 3, and multiply the first column in the second matrix, 3, 2. This is 1 times 3 plus 3 times 2, which is 3 plus 6, or 9. And lastly, we take the second row times the second column. 1 times 1 is 1, 3 times negative 1 is negative 3, 1 plus negative 3 is negative 2. This is the product of the matrix A times H. This product matrix has the dimension 2 by 2. Now this dimension comes from the number of rows in the first matrix and the number of columns in the second matrix. We can think of the same number of columns and rows canceled out, giving us the first number in the dimension of matrix A and the last number in the dimension of the matrix H.